Imagine a single isolated electric charge. It generates a steady, radiating electric field that pushes or pulls in a predictable sphere. In reality, charges don't exist in isolation. They are found in dense clusters, with millions of particles pushing and pulling on each other simultaneously. To understand this physics, we focus on a single coordinate in space, point P. We place 3 source charges around it. Point P becomes the center of a tug-of-war. With these overlapping forces, we must determine the net electrical effect here. Mapping this environment requires a systematic rule that allows us to deconstruct the system and solve for it one piece at a time. To solve for the net field, we freeze the environment and isolate just the first source charge, Q1. We define the distance and direction from that charge to our coordinate using a position vector, R1P. Using Coulomb's law, we calculate the electron field vector generated by Q1 alone. We represent this as E1, an arrow projecting from point P. This vector represents the exact force a unit positive test charge would experience if Q1 was the only source in the system. By isolating this single charge, we have established the first mathematical block of our environmental map. Now we reintroduce the remaining source charges to the grid. The principle of superposition states that these new charges do not alter or interfere with the field created by Q1. Our first vector, E1, remains exactly the same. Since these fields are independent, we calculate the vectors for charges Q2 and Q3 using the same isolated method. Point P is now acted upon by 3 independent vectors, each pulling or pushing in its own direction. To find the total effect, we add these vectors together using the tip-to-tail method. A final resultant vector, E of R, is drawn from point P to the end of the chain. This is the net electric field at our coordinate. This geometric addition is the physical reality behind equation 1.10. The formula is a summation of these individual, independent vectors across the entire system. This process isn't limited to a single point. It can be replicated at every coordinate in 3-dimensional space. By applying the superposition principle to the surrounding points, we calculate the net vector for the entire area. We map this space by drawing continuous field lines that remain tangent to these local vectors, revealing the flowing geography of the electrical environment. This completed map is a vector field. It allows us to predict how any object will interact with the system without needing to recalculate for every individual particle. When we drop a test charge into this field, it reacts instantly to these established rules, accelerating along the paths we've mapped. Solving a system with any number of charges comes down to this single additive process. Isolate the individual fields, calculate their vectors, and sum the parts.